Hi, I'm Reilly Innes, and this is a pre-recorded presentation for the 21st International Symposium on Aviation Psychology. My talk is on the effects of increased heads-up display information on cognitive workload in a simulated helicopter setting. This is work that I conducted with Zach Howard, Alex Thorpe, Ami Eidels, and Scott Brown at the University of Newcastle in collaboration with sensor company Hensoldt and aviation company Airbus. As technology has advanced over recent years, we've seen the amount of information delivered to operators increase tremendously. This can be exemplified by two of my dad's cars, where on the left, the 1960s Hillman Hunter has far less information presented than the Subaru on the right. Evidently, we now have the means to gain more information and deliver this to the operator. But is this always the best practice? In the current experiment, we worked with sensor company Hensoldt, who have developed sophisticated sensor technology, which can be delivered to helicopter pilots through their heads-up displays. The type of information delivered ranges from sort of basic metrics like altitude, horizon lines, and mountain ridge lines, through to fully contoured virtual environment mapping, highlighted obstacles, and landing markers. Typically, in a helicopter HUD, you may see information such as this displayed here. However, with the new sensor tech, we can deliver virtual environments more like this. There is more information here, which should help the pilots to operate more safely and effectively in worse conditions. However, we also need to account for the workload of the operator. So if the operator becomes overloaded due to the crowded visual display, this could have really significant negative consequences. When considering workload, we need to first question whether added information is affecting our performance. Then we should ask about workload. We might be able to fly better with added info, but are we actually sacrificing performance somewhere else? Or are we missing key information that we would otherwise observe? Here, we can use a simple behavioral experiment to measure operator workload and provide insight into these problems. It's important here to define workload and capacity. So our overall capacity is limited in that we can only do a certain amount of things at once before performance suffers. And this can relate to both cognitive or motor engagements. So cognitive workload refers to the amount of mental pressure you're experiencing, where tasks such as listening or reading require low levels of workload, whereas operating vehicles and multitasking require much higher levels of workload. Workload is limited by our overall capacity and is typically defined by the number and difficulty of the tasks at hand. To measure workload, we use the DRT, the detection and response task. The DRT measures leftover or residual capacity. It involves detecting a salient stimulus like a vibration similar to a mobile phone, and then responding via a button press as quick as possible. This happens many times throughout a task at a rate of about 3 to 5 seconds. And it's been used extensively in driver distraction studies in the US. It's important to remember that fast responses in the DRT mean that you have more residual resources and therefore a lower cognitive workload, and vice versa for slow responses. In our task, we asked trained helicopter pilots to fly a short route whilst undertaking the DRT across several environmental conditions. The different conditions vary the environment, like the time of day or the type of visibility, and the amount of information or symbology participants were shown. The 2D symbology related to generic HUD info that pilots are shown, and the 3D symbology related to the increased information of the new technology. Here, the key flight data for us was the landings. Here's a short video of the helicopter simulator where the experiment was conducted. As you can see, the simulator is a 210-degree immersive simulator with panels akin to those used in an MRH-90. You can see there in the front, the field that was the landing zone. So for the flight path, it was a horseshoe shape. It's shown here. The pilots were instructed to take off, and at this point, the DRT commenced. They were then asked to fly towards a mountain before turning and landing in the center of the field to make a horseshoe-shaped flight path. First, let's look at the flight results or landing results. For this, we use CEP as a measure of landing quality. These graphs show the target as the central cross and landings as the asterisks for each condition. The yellow circle indicates the circular error across landings. So here, remember that smaller CEP means more landings closer to the target. As you can see here, the top row, which are the daytime conditions, show the least error, as was expected. But more interestingly, the far right column shows the 3D symbology landings, which show the least error compared to their counterparts. So landings are better in easier flight conditions and improved with greater information shown, and there's also less variability. But what about workload? In this simple graph here, I'm showing average response times across environmental conditions, where higher response times indicate higher workload. Each line represents a different symbology condition. As you can see here, participants showed the highest workload in the dust condition, where they experienced brownout as they landed. We can also see the night condition requiring greater workload than the day conditions. When separating these out across the 9 scenarios, we can more clearly see that the 2D symbology consistently requires a higher workload, and that 3D symbology required less than 2D, but a greater workload than the nose symbology condition. This is interesting and shows that sometimes we may not require such high amounts of information if the scenario is more straightforward, as seen in the nose symbology conditions A and B compared to the 3D symbology conditions G and H. But in the 3D symbology condition, for the most difficult condition, condition I and C, which is the dust condition, we see a lower workload. Finally, these graphs show an example of workload variation across the duration of the flight for environmental conditions in the absence of symbology. I've only shown this nose symbology condition as it's a preliminary analysis with more work to come. In the top left, we see the day condition, where workload seems to increase slightly on the second half of the flight and coming into land. Compare this to the more difficult conditions, and we can see that at night, workload increases at the turning point and coming into land. And in the dust condition, in the bottom left, workload is high just prior to landing. We see these types of graphs as highly useful in future applications of DRT workload measurement, which could be combined with further performance measures. In conclusion, we should always test our technology with humans, as they are the key users. If workload of the user is too high, technology could pose unexpected risks to the operator. In this case, however, more information did generally lead to greater landing performance and came at no great cost to workload. We see this design as quite early stage, but feel there is great scope for future work in operator cognitive workload measurement. Thank you.